Hi everyone, welcome back to our lectures on quantum field theory, and this is part of chapter 9, symmetry breaking and Higgs mechanism. So by the way, before we continue, may I recommend you the book of Michio Kaku, Quantum Field Theory, Mandel and Shaw's Quantum Field Theory, and Gross's Relativistic Quantum Mechanics and Field Theory. Last time we talked about Lagrangians with a single particle. We determined its mass term through comparison to Klein-Gordon equation, and we also demonstrated how the spontaneous symmetry breaking was able to generate the mass of a particle, how it changes the vacuum energy or a vacuum state of a Lagrangian. So in this lecture, we will talk about Lagrangians with multiple particles and how these particles generate their masses, or were able to generate masses. So the spontaneous symmetry breaking of a Lagrangian will result in the appearance of more than one particle. Some of these particles may have mass and some may have zero mass or massless. They could have different masses as well, as we will be able to see in the electroweak theory. So first, we define a Lagrangian with two particles, with two real fields representing the particles here. So we will talk about a complex field applied to the Lagrangian, which gives rise to a massive and a massless particle. So again, we define the field in terms of two real fields, phi 1 and phi 2. And by the way, the symbolism here, I would use this kind of symbol to mean this one here, or vice versa, or sometimes I use this to mean the same thing. So anyway, I will just clarify it as I go through the lecture. So the Lagrangian here considered is this one. So in this case, you have a kinetic term, you have a mass term, and then you have a four-legged coupling coupled by coupling constant lambda. Now you have the field defined by phi 1, as you can, phi 1 minus I phi 2 plus I phi 2 over square root of 2, where the square root of 2 is just the normalization constant of the field. So if you get the phi adjoint times phi, then you would have this one. In this case, the phi adjoint would just be the complex conjugate of the field, the field composed of phi 1 and phi 2. So if we use that in the Lagrangian, our Lagrangian will become to look like this. From this Lagrangian, you can see the kinetic terms of phi 1 and phi 2, and also the mass terms of phi 1 and phi 2, and the other terms which are just the interaction terms. So if you look at the Lagrangian as well, you can see that the potential is given by this one. Given by this. Since this is the kinetic term, and so your potential would have to be given by this term. Which is just this one here. So it is very clear that the Lagrangian has phi 1, phi 2 symmetry that can be described by the rotation. That means exponential of an imaginary phase. This can now be written in matrix form. Here, sorry for that. Here. So you can write your phi 1 prime as cosine alpha phi 1 and sine alpha phi 2 plus, and phi 2 prime as negative sine alpha phi 1 plus cosine alpha phi 2. By the way, you can put the field phi 1 and phi 2 in front of the trigonometric function. So you can actually write this to avoid confusion. This is phi 1 cosine alpha plus phi 2 sine alpha, and this is negative phi 1 sine alpha plus phi 2 cosine alpha. So if you get the derivative of the potential with respect to phi 1 or phi 2, you will be getting the minima of the potential, which lie on a circle that is described by this one here. So you can get this from the derivative with respect to the fields. To break the U1 symmetry, we have to do the same method in the previous lecture, previous to this. We think again of a marble sitting at the top of the bowl, and then pick out a specific direction. And of course, when it rolls down, it will go to a certain minimum, and that minimum will be labeled as mu1, and the other one would have to be set to 0. So in this case, for simplicity, we pick the minimum at this. And the other one for the other field. So we will now rewrite the fields into some fields that fluctuates at this minimum. So we can rename the field, or we can assign the field chi and psi, such that the chi will fluctuate at m over square root of lambda, and the psi will just be fluctuating at 0. So our field is our phi will now be written as this. So the change in the coordinate system from phi 1, phi 2 to chi psi amounts to shift in the coordinate system to to the right by an amount m over square root of lambda. Now we can do some algebra to the shifted fields chi and psi, so that we can write phi 1 square into this expression, and of course phi 2 is trivial, and the quadratic terms become this expression also expanded into this one. So there are, in this case, 5 terms for phi 1, and of course phi 2 will just be psi to the 4th. And so if you put look at the expressions 1/2 lambda phi 2 and phi 1 square and phi 2 square, then you would have this expression. By the way, to emphasize, if you have phi to the n term where n is greater than 2, then those are just interaction terms. So if you want to get the mass, then just compare it with the Klein-Gordon equation, and then discard those terms with phi n, where n is greater than 2. By the way, constants can also be dropped from the Lagrangian. They don't actually affect the field. They don't contribute to the field equations. So now, dropping everything except the quadratic terms, the free parts of the potential are these ones here. So doing this and putting all these things together, we will have this is just the original Lagrangian in terms of phi 1 and phi 2, and then you have the Lagrangian. Now if you put your chi and your psi, it will look like this. This is just the free and non-interaction part of the Lagrangian. As you can see from there, you have a chi field which is fluctuating at non-zero minimum, has a mass there, has a mass term. However, your psi doesn't have mass. So as a conclusion, the spontaneous symmetry breaking of the U1 symmetry given by a rotation in phi 1, phi 2 space for the complex field that was given in equation 9.11, together with the Lagrangian in equation 9.12, gives the field chi with a mass m and the field psi as zero mass. The mass m is defined by the minima on the circle chosen to be initially chosen simply as m over square root of lambda, and so you can get lambda there to be square root of you can get m there to be square root of lambda times v1. This involves the use of scalar fields. So the particles associated with these fields are spin zero particles. So if that is spin zero, then we could compare it to a Klein-Gordon equation. The mass term there would be similar to the Lagrangian that we have. I mean the term, or I mean the mass term. So we now proceed with Higgs mechanism. So at this point, we have learned about spontaneous symmetry breaking, generating the mass of a particle. This time we will look at Higgs mechanism, where it will generate the mass of a vector boson, or the particle that results from a massless gauge field. So previously, spontaneous symmetry breaking was examined by considering the case of a complex field with two real components and a Ewing symmetry, and a global symmetry was considered. And now we extend this to a situation where a gauge field is included and a local gauge invariance under the U1 transformation is required. So here in this particular discussion, we consider a massless gauge field A mu, and we will show that symmetry breaking results in a massive vector field. And of course, this is done in getting the mass terms for W and Z bosons later on in the electroweak theory discussion, which is just the next lecture after this. So the Higgs mechanism involving spontaneous symmetry breaking involving a gauge field and local U1 invariance is known as Higgs mechanism. This is founded by, of course, the Nobel Prize winner Peter Higgs in 1964. But he was awarded later for the recent discovery of the particle of the God particle Higgs in the 2010s. So of course, the Large Hadron Collider discovered the Higgs-like particle, which is just the quanta of the Higgs field. In this discussion, symbolized by h of x field. So the global invariance states that the phi transforms into phi prime with this transformation, where theta is not dependent on space-time. But for a local one, we consider that the theta is dependent on space-time. So in this case, our transformation becomes specifically where theta is a function of space-time. By the way, Q here is just a number. So since we are now in a local gauge transformation, this will require the introduction of a gauge field. So again, the requirement for local gauge invariance forces to use a covariant derivative in order to restore the invariance of the Lagrangian. So we define a gauge field, a vector potential, A mu, and this A mu transforms this way. That is, it must also be invariant under U1 gauge transformation. We also have to note that the gauge field A mu is also a function of space-time. And now with the covariant derivative that we should consider for locally gauge invariant Lagrangian, here our Lagrangian now will look like in this form, where our f mu nu is just the product of this one here, the derivative of the gauge field. So if you look at the Lagrangian, it describes a complex scalar field with a massless gauge field, A mu, where A mu is present in f mu nu here. So later on, if we apply Higgs mechanism, we would have to see a contraction of A mu with a certain coefficient, and that would be then the mass of the gauge field. By the way, the Lagrangian is describing a theory that includes a complex scalar field phi in a massless gauge field A mu here. But in this discussion, we will see how Higgs mechanism puts on the mass of the massless gauge field. So if you look at the Lagrangian, going back, this is 9.19. So if you go back there, the potential is given by this. So by the way, in there's a constant nu that is to anticipate the search for a minimum. So in this case, nu is the minimum of the theory where the symmetry is unbroken. And now, seek the minimum potential energy when both the gauge field A mu and potential V vanish. When the symmetry is unbroken, the minimum of the potential, the vacuum state, is at nu, or phi square is nu, where it is a real number. So now we look at the gauge transformation. This is just the gauge transformation. So you can see that the phi is just equal to the phi square, I mean, is equal to nu. And so the local gauge transformation gives the same minimum. But if the field is complex, like what we did previously, there are infinitely many vacuum states, and we have to choose only one of those in the circle. So from here, since we saw that nu is the same minimum, then there is symmetry in that Lagrangian. But how is the symmetry broken? So the minimum is obtained with the squared amplitude of the complex field. So the symmetry can be broken by requiring that the field is real. So again, the local gauge transformation gives the same minimum. By the way, to be able to get the minimum here, you should be able to derive the potential with respect to either phi adjoint or phi. So again, how do we break the symmetry? So we will now we have the same minimum according to the gauge transformation, and when you derive the potential with respect to phi or phi adjoint. So the situation is that the value of V is the minimum of the potential when the symmetry is unbroken. So we need to find a transformation that gives the field in terms of the fluctuations about nu. So we can do that by doing this. So we retain the vacuum nu, and just we add a Higgs field on the nu. That would be the fluctuating field about the minimum here, just like what we did in the previous discussion. I mean, previous to this discussion, in the spontaneous symmetry breaking. So since of course your adjoint is real, so the potential becomes just this form. So now our covariant derivative will lead to the form and this one here. And of course, if you lower down the index, then you would have a negative part here. So the only thing that differs would be this sign from here. Therefore, when you multiply them, then you would have an expression of 4 terms. The first term here is the kinetic energy of the Higgs field. Then you would have here an expression that has these terms. So with this term and putting this together with the expression obtained for the potential in order to obtain the full Lagrangian for this particular system. So we as I'd like to repeat that we used a field that was chosen to be real that fluctuates on the minimum, that is Hx, that is the Higgs field that we have chosen. So if you put everything now to the Lagrangian, you will have this. So we have this term for the kinetic term for the Higgs, and then you have mass for the Higgs field. And then we can also see that there is this term as well, and this looks like a mass for the gauge fields. So anyway, let's proceed. So you can see that the free Lagrangian of the Higgs would look like this, and so it has a mass, and then of course the mass would be accounting the 1/2, the missing 1/2 there would be square root of 2 times m. So there you have the Higgs field as a scalar with spin 0, boson with spin 0, and that is a boson with square root of 2 times m mass. And for the free Lagrangian of the gauge field, we call them B here for bosons, and it will give you this terms, and of course the additional term q square, nu square, a nu, a mu. By the way, prime here should be drop the primes. So in this case, initially your f mu nu was present in the original Lagrangian, but this time after Higgs mechanism you have a term that has a term that represents the mass of the gauge field. So here we have a mass that is equivalent to this. The other term would just be self-interaction terms of the Higgs. This one is a three-legged interaction, while this one is a four-legged Higgs self-interaction. And you have also an interaction term representing coupling between the Higgs field and the gauge field, which is just this one. So this is a three-legged interaction involving the gauge field and the Higgs. They are the terms here. This one and this one. So as a summary, I'll just read the tabs here. Spontaneous symmetry breaking is a process which leads to the appearance of massive particles in the Lagrangian. The procedure works by considering a Lagrangian with some vacuum state. The system is then reconsidered by breaking the symmetry, leading us to a new vacuum state. Gauge invariance leads to the appearance of new particles. Now, for a scalar theory, a massive Goldstone boson appears. When a complex scalar theory is combined with a massless gauge field, breaking the symmetry by forcing a field to be a real fluctuation about the unbroken vacuum V leads to the appearance of a massive scalar field called the Higgs field and the gauge field acquired mass. We will see more of this in the electroweak theory when we discuss it in the next video, in the next lecture. And the Higgs field and the gauge field are coupled through an interaction Lagrangian. So you can also read the quiz here. Maybe you can answer some of them. So that's it for this chapter. I hope you've learned something, and the problem set will be given after this.